Good day, dear colleagues. The topic of this presentation: simulation of a mission with a low-Terra spacecraft to near Earth asteroid. I will talk for about 50 minutes. I divided my presentation into 4 sections. At first, I will state the problem of the mission. Then, I will speak about mathematical model of controlled motion. After that, I will tell about choosing the method of optimal control. And finally, I will speak about result. The paper analyzes the optimal transition between non-planar orbits of a non-satellite with low thrust engines. Since the spacecraft has a single engine, the acceleration from the thrust of the engines is constant in magnitude and directed along the binormal or transversal. The aim of this work is to develop a method for modeling the controlled motion of a spacecraft with low thrust engines for non-planar flight between low Earth orbit and the orbit of a near Earth asteroid 2016 HO3. This slide presents characteristics of the asteroid 2016 HO3. This asteroid whose diameter doesn't exceed 100 meters. It is assumed that the asteroid 2016 HO3 moved in the same orbit with the Earth around the Sun until about 100 years ago. It was captured by Earth's gravity. Many astronauts at first even considered its space debris a piece of some car rocket. The asteroid moves around the Sun in elliptical orbit and simultaneously in an elliptical orbit around the Earth. Also, the orbit is slightly tilted relative to the Earth, so it goes up and down. On this slide, we can see orbit of asteroid 2000 HO3 in rotary geocentric frame. On figure A, we can see orbit of asteroid in elliptical plane, and figure B in polar plane. Under the action of low thrust, the motion of the spacecraft can be described by Newton's equations of the theory of perturbed motion, where U is the argument of latitude, A is the semi-major axis, lambda 1 and lambda 2 are the components of the Laplace vector, epsilon is the eccentricity, P is the focal parameter, omega is the argument of periapsis, I is the inclination, tau is the epoch, theta is the true anomaly, T is the current time, A is the acceleration vector with its component in orbital frame. The long duration of the controlled process and the cyclical changes in the phase coordinates determine the feasibility of the transition to the override equations. To carry out the overriding procedure, we move from the derivatives of the escalating elements in time to the derivatives of the latitude argument. The system of equations 1,6 will take the form of equation 7 13. We design research mission and development means of countering asteroid danger. The problem arises of development control schemes for spacecraft in the fields of attraction asteroids as objects with a complex geometric shape. The force of gravitational interaction of elementary masses in such cases is insufficient for the formation of bodies of about regular geometric shapes, for example, ellipsoid of spheroid surfaces. Complex geometry produces a gravitational field of complex configurations. On this slide, we can see a variety of asteroid shapes. Due to the need to maintain the orientation of the spacecraft relative to the asteroid, the use of thrust directed along the radius vector is difficult, and in the future it is assumed that two accelerations are used for control: binormal and transversal. Using this, we get a transform system of equation 7, 13 to the system of equation 14, 19. To determine the optimal control structure on the term, we will solve the problem of the shortest flight duration. Following the maximum principle, it is necessary to select such coordinates of the switching points of the engine UE that deliver the maximum to the Hamiltonian. We write the Hamiltonian in the form presented in equation 22. Since H0 doesn't depend on the control, the maximum of the Hamiltonian under the technical restriction 20 is achieved under the following conditions. The graphs of the function h tau of u and hn of u are sinusoid with the same period presented on the first picture. Therefore, to ensure the maximum of the Hamiltonian, there must be no more than 4 engine switching point on the term. For example, for a certain point in time, for the values h tau of u and hn of u shown in first picture, the control structure on the turn will have the form as shown in second picture. After performing the integration and denoting u1, u2, u3, u4 as the arguments of the latitude of the engine freezing point and going to the slow time t, length in u variable, the override equation will have the form 24, 29. When constructing an algorithm for controlling the spacecraft motion with low thrust, it is necessary to take into account that every small perturbation first leads the significant deviation of the device from the calculated trajectory. It is now that the influence of the non-spherical Earth's gravity fields is mainly described by the second term of the expansion of the gravitational field potential in the spherical function. Therefore, the long change in the orbital elements due to the influence of corrective acceleration and the influence of the off-center gravity field of the Earth can be described by the following system of equation 34. Let's write the boundary condition as equation 35. We formulate a variation time optimal problem about the interorbital transfer. It is necessary to choose the controlled function u e of t, which provides the transfer of the state point from the position x0 to the position x1 in the minimum of time under the differential equation of motion 34 and boundary condition 35. The acceleration value a0 is considered to be set. Let's solve the problem using the Pendragon maximum principle. Let us introduce the co-state vector psi and construct the Hamiltonian in equation 36. The Hamiltonian maximum condition we find of system equation 37 for t. Let's write a co-state system in system equation 31, 36. The start orbit of spacecraft is a near-polar circle-low Earth orbit with state vector x of t0. Asteroid 2016 HR3 is selected for calculation. This picture shows the variation of the orbital elements of the asteroid from H of May 2021 to H of June 2021. This data was used as the required orbital elements at the flight finish x of t1. On this slide, presented integration of motion equation and conjugate system of equations. In conclusion, today we considered the problem statement, the mathematical model of controlled motion, chose the method of optimal control, and results. Thank you for your attention, and I will be happy to answer the questions.